Most of us look up at the night sky and feel like we're seeing the universe. On a truly dark night, far from city lights, you might pick out a few thousand stars. Quiet points of light that seem calm, evenly scattered, almost still. But here's the first thing to know. Every star you can see with your naked eye belongs to the Milky Way. None of them are from Andromeda. None of them are from the deep, distant galaxies beyond our own. What feels like the cosmos is actually just a thin sample of our local home. And even then, we're missing most of it. Not because the Milky Way is empty, but because our eyes were never built for that kind of scale. Huge regions are hidden behind dust and gas. Countless stars are too faint, too far, or packed into crowded layers of light we can't separate. So the sky that looks open and simple is really a dense structure with depth. A galaxy made of hundreds of billions of stars in constant motion. We don't stand outside the Milky Way, looking in. We are inside it. A rotating system more than 100,000 light years across. And from our position, we only catch a narrow slice. Tonight, we're going to trade that illusion for something clearer. A sense of where we are and what surrounds us. To understand where we are, we first need to leave what feels familiar. When we imagine space, we often picture it as empty. A vast, silent void stretching endlessly between stars. But the space between stars is not truly empty at all. It is filled with thin traces of hydrogen gas, drifting dust, and high-energy cosmic rays. Particles moving so fast and carrying so much energy that they can damage cells, strip atmospheres, and slowly erode the conditions life depends on. And yet, here, around our sun, life has had time to grow. That's because the solar system does not sit unprotected in this environment. The sun is constantly releasing a stream of charged particles known as the solar wind. This wind flows outward in all directions, far beyond the orbits of the planets, creating a vast, invisible bubble around us. This bubble is called the heliosphere. The heliosphere acts as a shield. It bends and deflects a large portion of incoming cosmic radiation, reducing the amount that reaches the inner solar system. Without it, Earth would be exposed to far harsher conditions, and the long, stable history required for life may never have been possible. Even at the outer edges of our planetary neighborhood, beyond Neptune and into the Kuiper Belt, the sun's influence still dominates. Icy worlds and frozen debris drift there, marking the distant boundary between familiar space and something far less forgiving. What makes this remarkable is how fragile the balance truly is. The heliosphere isn't solid. It isn't permanent. It exists only as long as the sun continues to breathe outward into space, holding back the pressure of the surrounding galaxy. Life on Earth may depend on a structure no one can see, shaped by particles too small to notice, yet powerful enough to define the conditions of an entire world. For now, we remain inside this protective bubble, moving with it, sheltered by it, and rarely aware of it. But every shield has an edge, and beyond that edge, the rules of the galaxy begin to change. For most of human history, the solar system felt endless. Beyond the planets, beyond the distant ice and debris, it was easy to imagine the sun's influence simply fading into infinity. But in reality, the solar system does have an edge. As the solar wind streams outward from the sun, it eventually begins to slow. This happens when it meets the pressure of the interstellar medium, the thin gas and particles that fill the space between stars. The first sign of this slowdown is known as the termination shock. Here, the solar wind abruptly loses speed. no longer able to push freely against its surroundings. Beyond that lies the Helios sheath, a broad, turbulent region where the solar wind is compressed, twisting and folding as it struggles to maintain its outward flow. This space is neither fully solar nor fully interstellar. It is a transition zone, restless and unstable. And then, farther still, comes the heliopause. The heliopause marks the outer boundary of the sun's influence, the place where the pressure of the solar wind is finely balanced by the pressure of interstellar space. At roughly 18 billion kilometers from the sun, this boundary forms the true edge of the solar system. But it is not a wall. There is no sudden darkness, no visible line, no signpost marking the moment you leave home. The heliopause shifts and breathes, expanding and contracting as solar activity rises and falls. It is a living boundary, shaped by forces on both sides, constantly in motion. Crossing it doesn't feel dramatic, it feels quiet. Yet passing this invisible line means something profound. The sun no longer dominates the environment around you. Its protective bubble has ended. Beyond this point, the solar system gives way to the wider galaxy, a place governed by different pressures, different radiation, and a different sense of scale. And long before we ever understood this boundary, something small and human was already on its way toward it. In 1977, 2 small spacecraft left Earth with no promise of return. They were called Voyager. Voyager 1 was never designed to travel forever. It was built to study the outer planets, to send back images of Jupiter's storms, Saturn's rings, and the distant edge of our planetary neighborhood. But after completing its mission, Voyager didn't stop. It kept moving, year after year, decade after decade. It drifted farther from the sun than anything humanity had ever sent before. More than 30 years passed before Voyager 1 finally reached the region where the sun's influence begins to fade and the space between stars takes over. On board, Voyager carries something fragile and deeply human. A golden record. Etched into it are sounds of Earth. Wind, rain, ocean waves, footsteps, laughter, music. Voices speaking greetings in dozens of languages. A quiet introduction to who we were and where we came from. And with Voyager's passage into interstellar space, the stars ahead are no longer just distant lights in the sky. They are places we have already begun to reach toward. Once we leave the solar system behind, the galaxy stops feeling abstract. Stars are no longer just points of light. They become destinations, places with distance, structure, and consequence. Astronomers call this region our stellar neighborhood, the small collection of stars closest to the sun as it moves through the Milky Way. And the nearest of all is Alpha Centauri. Alpha Centauri is not a single star, but a system of 3, located about 4.37 light-years from Earth. On a galactic scale, that is remarkably close, yet even this short distance is difficult to grasp. Alpha Centauri A and B form a tight binary pair, locked in a slow orbital dance that takes about 79 years to complete. At their closest, the 2 stars pass within roughly 11.2 astronomical units of each other. At their farthest, they drift apart to about 35.6 astronomical units. Alpha Centauri A is slightly larger and brighter than our Sun, a familiar kind of star burning steadily. Alpha Centauri B is smaller and cooler, but still stable, still long-lived. Together, they resemble a quieter version of our own stellar home. The third member of the system, Proxima Centauri, orbits much farther out, loosely bound to the pair. It is smaller, dimmer, and far more active. A reminder that even nearby stars can be very different from the Sun. What makes Alpha Centauri feel so close is comparison. No other star system lies nearer. No other suns are closer neighbors. And yet, this is where the illusion breaks. 4.37 light-years means light itself takes more than 4 years to cross the gap. For spacecraft built by humans, the journey would take tens of thousands of years. Even the fastest probes we have ever launched would barely make progress on that scale. So Alpha Centauri is close only in an astronomical sense, not in a human one. It sits just beyond reach, close enough to study, close enough to imagine, but far enough to remind us of our limits. If these are the stars nearest to our own, then the rest of the galaxy, with its hundreds of billions of suns, lies at distances that stretch far beyond intuition. And orbiting one of those nearby stars is a world that quietly changed how we think about life. Orbiting far beyond Alpha Centauri A and B is a much smaller, dimmer star. Its name is Proxima Centauri. Proxima is a red dwarf, the smallest and coolest type of star capable of sustaining nuclear fusion. Its surface temperature is only about 3,100 Kelvin, roughly half that of the Sun. From Earth, it's completely invisible to the naked eye, too faint to stand out even on the darkest night. Yet stars like Proxima are everywhere. Red dwarfs are the most common stars in the Milky Way. They outnumber stars like our Sun by a wide margin, filling the galaxy quietly and abundantly. And unlike larger stars, they burn their fuel with extreme efficiency. While the Sun will shine for about 10 billion years in total, red dwarfs can remain stable for trillions of years, outliving almost every other type of star in the universe. In many ways, they seem ideal. But Proxima Centauri carries a complication. It is a flare star. Without warning, Proxima releases powerful bursts of energy, sending intense X-rays and ultraviolet radiation outward into space. These flares can be far stronger, relative to the star's size, than anything our Sun produces. For planets orbiting close by, this activity matters. Repeated exposure to high-energy radiation can strip atmospheres, disrupt chemistry, and make long-term stability difficult, even if temperatures appear suitable at first glance. This is the paradox of red dwarfs. They are small, long-lived, and abundant, yet often restless and unpredictable. A star that can shine for trillions of years can still be harsh to the worlds that circle it. Proxima Centauri reminds us that size alone does not determine influence. A small star can shape its surroundings in profound ways, especially when planets orbit close enough to feel every outburst. And despite all of this, despite the radiation, the flares, and the instability, astronomers found something around Proxima that few expected to discover so close to home. In 2016, astronomers confirmed a planet around the closest star to the Sun. It was called Proxima b. At first, the numbers sounded almost comforting. Proxima b was estimated to have about 107% the mass of Earth, a super-Earth that is likely rocky. And it orbits Proxima Centauri once every 11 Earth days at a distance of about 0.049 AU. That distance is hard to picture. So here's a simple comparison. Proxima b is more than 20 times closer to its star than Earth is to the Sun. In the most basic sense, that puts it in the star's so-called habitable zone, the range where temperatures could allow liquid water, if water exists at all. But this is where the word habitable starts to become misleading. Because when a planet orbits that close, it may become tidally locked, like a cosmic version of the Moon's relationship with Earth. One side could face the star forever. The other could remain in permanent night. In theory, that might create a narrow twilight band, a place where temperatures are less extreme. Some ideas even suggest that liquid water could exist on the night side, or along that thin dividing line. But Proxima Centauri is not a quiet host. It is a flare star. Its bursts of high-energy radiation, X-rays and ultraviolet, can surge outward repeatedly, sometimes multiple times a day. And for a planet sitting only 0.049 AU away, those flares are not a background detail. They are the environment. There's another effect most people don't think about at first. Tides. Tides don't just pull oceans. They can also pull an atmosphere. Because Proxima b sits so close to its star, its atmospheric tides may be up to 500 times stronger than Earth's. That kind of constant gravitational kneading can stress a planet's long-term stability, even if the surface remains solid. So Proxima b becomes a lesson in realism. A world that is close and Earth-like in mass, and still potentially harsh. Not because it's the wrong size, but because its star dominates everything. Then there is Proxima d. Discovered later, Proxima d is far smaller, about 25% the mass of Earth. It completes an orbit in just 5 Earth days, and it circles at a distance of roughly 3% of Earth's distance from the Sun. That places it so close that habitability, in any normal sense, is unlikely. But scientifically, it matters. It shows how tightly packed these systems can be around red dwarfs. And finally, Proxima c. This one has carried more debate because its story has changed over time. It is often described as a mini Neptune, roughly 7 times the size of Earth, orbiting far from the star at around 1.5 AU, taking about 1/900 Earth days to complete one orbit. By temperature alone, it would be bitterly cold, estimated around 233 degrees, far outside any habitable range. But what made Proxima c fascinating wasn't comfort, it was confirmation. Images from the Hubble Space Telescope, taken back in 1995, were later used to help support the case for its existence, making it one of the rare exoplanet candidates with a form of visual backing, not just indirect measurements. So when you hear closest exoplanets to Earth, it's tempting to imagine the closest new homes. But the Proxima system doesn't offer a simple fairy tale. It offers something more useful, a correction. The habitable zone is only a temperature guideline. It does not guarantee an atmosphere. It does not guarantee oceans. It does not guarantee protection from radiation. And it certainly does not guarantee life. If this is what we find at the nearest star, a handful of worlds shaped, stressed, and defined by their host, then the challenge of reaching truly welcoming places is not just a matter of distance. It's a matter of crossing that distance in the first place, and doing it with ideas far beyond anything Voyager could ever attempt. The distance to Alpha Centauri sounds small until you measure it properly. The nearest star system lies about 4.37 light-years away. That translates to roughly 23.5 trillion miles, or 37.8 trillion kilometers of empty space. At the speed of Voyager 1, the fastest spacecraft humanity has ever flown, that journey would take more than 70,000 years. So for most of modern history, interstellar travel wasn't difficult. It was simply irrelevant. Then, in the last decade, that assumption quietly began to change. The idea is called breakthrough starshot. Instead of sending a large spacecraft, Starshot proposes something radically smaller. A fleet of nanocraft, each weighing only a few grams. Attached to each is a light sail, just meters across, thin enough to be pushed by photons themselves. The engine isn't carried on board. Instead, the proposal calls for a ground-based laser array, capable of delivering roughly 100 gigawatts of power, about the output of dozens of large power plants combined, focused onto the sail for a few minutes. In theory, that burst would accelerate the craft for about 10 minutes, pushing it to nearly 20% the speed of light, around 60,000 kilometers per second. At that speed, the journey to Alpha Centauri would take approximately 22 years. For the first time in history, a trip to another star could fit within a human lifetime. But this is where imagination has to slow down. At 20% light speed, even tiny dust grains become dangerous. A particle the size of a grain of sand would strike with the energy of an explosive. Shielding a craft that small without adding mass remains an unsolved problem. Navigation is another challenge. At those velocities, even a minor error early on could mean missing the entire star system by millions of kilometers. There would be no chance to correct course once the acceleration phase ends. And even if everything worked perfectly, even if a nanocraft reached Alpha Centauri intact, it wouldn't stop. It would pass through the system in hours or days, taking images and measurements as it flew by. Then comes the hardest part: sending the data home. At a distance of 437 light-years, any signal sent back would take more than 4 years to reach Earth. The power required, the precision of the antenna, and the durability of the electronics all remain open questions. Because of this, Breakthrough Starshot is not a mission. It is a concept, a test of whether physics allows interstellar travel without waiting for technologies that may never arrive. What makes it remarkable is not that it guarantees success, but that it reduces the problem to something finite. Not tens of thousands of years, not geological time, but decades. Still, even at its fastest, Starshot reminds us of a humbling truth. 22 years is quick by cosmic standards. By human standards, it is still a lifetime of waiting. The project sits at a boundary between what we can imagine and what we can responsibly attempt. If humanity ever leaves its stellar neighborhood, it will likely begin with ideas like this: small, fragile, and uncertain, pushed forward not by engines, but by light itself. And even if we never reach another star, the galaxy has not stopped moving. It is already carrying us, slowly, steadily, toward places we have not yet learned how to see. When we talk about the Milky Way, it's easy to imagine extremes: the violent core at the center or the vast emptiness far beyond the spiral arms. But between those extremes lies something quieter. Astronomers call it the local stellar neighborhood, the region of space within about 20 light-years of the Sun. It sounds small. It isn't. Within that modest distance are roughly 131 stellar objects, single stars, binary systems, and faint red dwarfs drifting in slow motion. Yet from Earth, only 22 of them are bright enough to be seen with the naked eye. Most of our closest neighbors are completely invisible to us. One of the most revealing examples is Barnard's star. Located about 5.95 light-years away, Barnard's star is one of the nearest stars to the Sun, and also one of the oldest. Estimates place its age at around 11 to 12 billion years, more than twice the age of our own Sun. It is a red dwarf, small and faint, with a long and quiet life behind it. But quiet does not mean inactive. Evidence suggests Barnard's star experienced flare activity in its past, a reminder that even ancient stars can shape their surroundings in unpredictable ways. In 2018, astronomers detected a planet orbiting this old star. The planet has a minimum mass of about 3.2 times that of Earth and completes an orbit every 233 days. By distance alone, it lies well outside the star's habitable zone. Temperatures there would be far too cold for surface liquid water. Barnard's star shows us something important. Age does not guarantee gentleness, and proximity does not imply comfort. Then there is Sirius. On a clear night, Sirius dominates the sky, the brightest star visible from Earth. It sits about 6 light-years away and feels familiar simply because we see it so easily. But Sirius is not a single star. It is a binary system. Sirius A is a bright, massive star, about twice the mass of the Sun. Orbiting it is Sirius B, a white dwarf, roughly the size of Earth, but containing nearly the Sun's mass. Sirius B is the dense core of a star that has already died, a stellar remnant packed into a sphere only a few thousand kilometers across. It is one of the closest examples we have of what awaits many stars at the end of their lives. Together, Barnard's star and Sirius reveal a pattern. The stars nearest to Earth are not uniform. They vary wildly in age, mass, behavior, and history. Some are ancient and dim. Some are bright and unstable. Some carry planets. Some carry the remnants of stars long gone. Closeness does not mean safety, and familiarity does not mean simplicity. The quiet neighborhood around the Sun is anything but static. Stars drift, systems evolve, and environments change. Slowly, silently, and without regard for human timescales. Even here among the stars we call near, motion never truly stops. And as they move, these stars will continue to reshape the space around us. Sometimes gently, sometimes in ways we have yet to experience. Stars do not stay where we first find them. Inside the Milky Way, every star follows its own path, orbiting the galactic center, drifting relative to its neighbors, slowly changing the shape of local space over millions of years. The Sun is no exception. As it moves through the galaxy, other stars occasionally pass nearby. Not close enough to collide, but close enough to matter. According to stellar motion models, about 694 stars are expected to pass through our region of space within the next 15 million years. Of those, 26 may approach closer than 3.3 light-years. On human timescales, that sounds impossibly distant. On galactic timescales, it is routine. Most of these encounters will pass unnoticed. But some occur close enough to disturb the outermost edges of the solar system. Far beyond the planets, past the Kuiper Belt, lies a vast and tenuous reservoir known as the Oort cloud. The Oort cloud is not a solid shell. It is a loose halo of icy debris, trillions of frozen remnants left over from planet formation, stretching tens of thousands of astronomical units from the Sun. These objects are barely held in place. Their orbits are fragile, maintained by a delicate balance of gravity. And that balance can be disrupted. When a star passes nearby, its gravity can tug at the Oort cloud, nudging long dormant objects onto new trajectories. Some are sent outward, lost to interstellar space. Others are redirected inward, becoming long-period comets that fall toward the inner solar system. This is not speculation. It is a known mechanism. One of the clearest future examples already has a name: Gliese 710. This star is currently approaching the Sun and is predicted to pass by in approximately 1.29 million years. At its closest point, it may come within about 10,520 astronomical units, deep inside the outer Oort cloud. That distance is far beyond the planets, but close enough to matter. Simulations suggest Gliese 7 to Hendon's passage could trigger a significant comet disturbance, what astronomers sometimes describe as a comet shower. Some estimates suggest this could increase the number of visible long-period comets to around 10 per year, far more than we typically see today. This does not mean catastrophe is inevitable. Most comets never reach Earth. Most pass harmlessly through the inner solar system before returning to the dark. But the process itself is revealing. The greatest long-term influences on Earth's environment do not always come from dramatic explosions or distant supernovae. They can come from slow, silent encounters. A star passing close enough to whisper through the edges of our system. The galaxy shapes our future not through sudden violence, but through gradual motion. The sun moves, other stars move, and the solar system travels with them, through regions that are never truly empty, never truly still. As these stellar neighbors drift past, they remind us of something easy to forget. Even in the quietest parts of the Milky Way, we are part of a much larger environment, one that is always in motion, always unfolding, and never entirely predictable. Beyond the heliosphere, space does not suddenly become uniform. The environment around the solar system has structure, layers, boundaries, and regions with very different conditions. Right now, the sun is moving through a region known as the local interstellar cloud. It is a diffuse cloud of gas, roughly 30 light-years across, made mostly of hydrogen and helium, with traces of heavier elements drifting between the stars. The solar system is not stationary within this cloud. It is passing through it, slowly, steadily, carried along by the sun's motion around the Milky Way. But the local interstellar cloud itself is only a small part of something much larger. Surrounding it is a vast, low-density region called the local bubble. The local bubble spans nearly 1,000 light-years in diameter. Compared to typical interstellar space, it is unusually empty. Its gas density is far lower than average, and its interior is filled with hot, thin plasma. Astronomers believe this bubble formed about 14 million years ago, likely carved out by a series of supernova explosions from massive stars that once lived nearby. Those explosions swept surrounding gas outward, leaving behind a hollowed region in the galaxy. The Sun entered this environment relatively recently, around 5 million years ago. That timing matters. A lower density region means fewer high-energy particles, less interstellar pressure on the heliosphere, and a more stable boundary between the solar system and the galaxy beyond. In subtle ways, this environment may influence what reaches Earth, from cosmic radiation levels to the long-term stability of conditions near our planet. It is not a shield in the way the heliosphere is, but it is a gentler neighborhood, a quieter stretch of the galaxy. From this perspective, Earth does not simply orbit the Sun. The entire solar system is traveling through a specific galactic landscape, one that happens to be unusually calm. As many astrophysicists have noted, the Sun is traveling through a uniquely low-density region of the galaxy. That does not mean our location was chosen. It does not imply design. But it does suggest that where we are matters. Life on Earth exists not only because of the planet itself, or even because of the Sun, but because of the broader environment we are passing through. A rare pocket of relative quiet inside a much more active galaxy. This calm will not last forever. Beyond the boundaries of the local bubble, the Milky Way becomes denser, more turbulent, and far more energetic. And as we move outward from this gentle region, the galaxy ahead begins to reveal a very different character. Beyond the quiet bubble we now travel through, the Milky Way changes its character. Gas thickens, dust gathers, and gravity begins to pull matter together with purpose. One of the clearest places to see this is the Orion region, located about 1,344 light-years from Earth. It lies along the Orion arm of the galaxy, a part of the Milky Way where star formation is still actively unfolding. Unlike the calm surroundings of our solar system, Orion is busy. Massive clouds of gas and dust collapse under their own weight, heating up, fragmenting, and igniting new stars in a process that has been repeating for billions of years. One of the most recognizable stars in this region is Betelgeuse. Betelgeuse is a red supergiant, a star nearing the end of its life. Its diameter is estimated to be about 700 times that of the Sun. Large enough that if it replaced our Sun, it would extend beyond the orbit of Mars. With a mass roughly 10 to 20 times that of the Sun, Betelgeuse burns its fuel quickly. Astronomers expect it will eventually explode as a supernova. Not tomorrow, not next year, but sometime in the distant astronomical future. Betelgeuse reminds us that in Orion, stars are not only being born, they are also dying, returning material to space that will one day form new stars and planets. At the heart of this region lies the Orion Nebula, also known as M42. The Orion Nebula is a stellar nursery about 2 million years old, extraordinarily young by cosmic standards. It spans roughly 30 to 40 light-years across and contains dense pockets of gas, where thousands of stars are actively forming right now. Inside these clouds, gravity competes with radiation, shaping disks of material around newborn stars. From those disks, planets may eventually emerge. What we are seeing in Orion is not a snapshot of the past. It is a process still underway. Recent observations from the James Webb Space Telescope have revealed something even more surprising. In the Orion region, Webb identified 540 planetary mass objects. Bodies with masses comparable to Jupiter that appear to be drifting freely through space. Some of these objects are found in pairs, so-called binary Jupiter mass objects, suggesting they form together without ever orbiting a star. This challenges long-standing assumptions about how planets come into existence. If planetary mass objects can form directly from collapsing clouds without a parent star, then the line between star and planet becomes less clear. In some regions of the galaxy, these free-floating worlds may even outnumber stars themselves. Orion shows us the Milky Way as a living system. Stars are not static points of light. They are part of a continuous cycle: birth, evolution, and death, all happening on scales too slow for human senses, yet constant on galactic timescales. While Earth sleeps, new stars ignite in Orion. New worlds take shape in clouds we can barely see, and massive stars quietly prepare for endings that will reshape their surroundings. Compared to this activity, our corner of the galaxy feels unusually calm. That contrast is not accidental. It is part of a much larger structure. One that stretches across spiral arms, connects star-forming regions to quiet zones, and organizes the Milky Way as a whole. To understand where Orion truly fits, we need to step back even further and see the galaxy not as a collection of regions, but as a single, rotating system with patterns that guide where stars form, where life might endure, and where calm can exist at all. From a distance, the Milky Way is often imagined as a simple, flat disk, a glowing pinwheel frozen in space. But the real structure of our galaxy is far more complex. The Milky Way is a barred spiral galaxy. At its center lies a dense bar of stars, and from that bar extend sweeping spiral arms that curve outward across tens of thousands of light years. This picture did not come easily. Because we live inside the Milky Way, dust and gas block our view in visible light. Only with infrared observations, including data from the Spitzer Space Telescope and careful mapping of gas and young stars, did astronomers confirm the galaxy's true shape. Those spiral arms are not rigid structures. They are not fixed lanes of stars. They are density waves, regions where gas and stars crowd together temporarily as they orbit the galactic center. As material drifts into a spiral arm, it becomes compressed. That compression triggers star formation. Then, over time, stars drift back out again, leaving the arm behind. This is why spiral arms are active, luminous regions, and also why they are unstable over long time scales. As NASA has put it, spiral arms are regions of higher density, not fixed structures. Among the major arms are the Alpha Centauri arm, stretching roughly 55,000 light-years in length and about 1,000 light-years across, and the Perseus arm, which extends for more than 60,000 light-years with a similar width. There are also secondary arms, including the Norma arm and the Sagittarius arm, adding further complexity to the galaxy's structure. Nothing about this arrangement is static. The arms shift, their shapes evolve. The Milky Way is a moving system, not a stable map etched into space. And within this motion, the solar system occupies a very specific position. We do not live in one of the Milky Way's main spiral arms. Instead, the Sun resides in a smaller structure known as the Orion arm, sometimes called the local arm, a quieter spur between the larger Perseus and Sagittarius arms. Estimates place the Orion arm at roughly 10,000 light-years in length, with some studies suggesting it may extend beyond 20,000 light-years. It is not empty, but it is less crowded, with fewer massive stars and fewer violent events. Our distance from the galactic center is about 26,000 light-years, far enough to avoid the intense radiation and frequent supernovae near the core, yet close enough to benefit from the heavier elements produced by generations of stars before us. This balance is not trivial. Too close to the center, and dense star populations increase the chances of catastrophic radiation events. Too far out, and there may not be enough heavy elements to build rocky planets at all. The Orion arm sits between these extremes. It is a region with fewer close encounters, fewer disruptions, and long-term gravitational stability. Conditions that allow planetary systems to remain intact for billions of years. In that sense, our location is quietly remarkable. Life on Earth does not exist only because of the planet's distance from the Sun or the presence of liquid water. It exists because the solar system occupies a relatively calm corridor inside a galaxy that is anything but calm. As astrophysicist Guillermo Gonzalez has noted, location within a galaxy may be just as important as location around a star. The Milky Way is full of motion, compression, and energetic change. Yet we are not at the center of that activity. We are not in the safest place possible. But we are in a place where complexity had time to grow. Not by chance alone, but because of where we are allowed to persist. We are not at the center. We are not at the edge. We are not in the quietest location imaginable. But we are in the right one. And that realization leads to a larger idea. One that moves beyond individual planets and begins to consider where life can endure on the scale of an entire galaxy. When we talk about habitability, we usually think small, We imagine a planet at the right distance from its star, with liquid water on its surface and a stable atmosphere overhead. But over time, astronomers began to realize that this idea doesn't go far enough. Because planets do not exist in isolation, stars do not exist in isolation, and life, if it is to last, must survive not just local conditions, but the environment of an entire galaxy. This led to a broader concept, the Galactic Habitable Zone. It describes regions of a galaxy where conditions may allow life to develop and persist over billions of years. Near the center of the Milky Way, stars are packed closely together. Supernova explosions are more frequent, radiation levels are higher, gravitational interactions are stronger. In such crowded environments, planetary systems are more easily disrupted, and long-term stability becomes difficult to maintain. Far from the center, a different problem emerges. The outer regions of the galaxy contain fewer heavy elements. The materials needed to build rocky planets, complex chemistry, and potentially biology. Stars form more slowly there, and planetary systems may never gain the ingredients required for life as we know it. Between these extremes lies a narrower region, not too close, not too far. A zone where heavy elements are abundant enough to form solid worlds. Yet violent events are rare enough to allow long stretches of calm. This is the Galactic Habitable Zone. Our solar system lies close to the middle of this region, not at its safest point, but well within the range where planetary systems can remain intact for billions of years at a time. That time is essential. Life does not appear quickly. On Earth, it took hundreds of millions of years for the earliest forms to emerge, and billions more for complexity to develop. Without long-term stability, without a galaxy that stays relatively quiet, biology may never get the chance to begin, let alone endure. This reframes our place in the universe. Earth is not special because it orbits the sun. The sun is not special because it is a single star. Our survival may depend on something larger, where this entire system sits inside a vast, evolving galaxy. From this perspective, most of the Milky Way may be hostile to long-term life, not because it is empty or barren, but because it is too active, too crowded, or too chemically simple. The galaxy itself shapes biological destiny, slowly and indirectly, through patterns that unfold over billions of years. We live in a region where the galaxy gives life time. Time to stabilize, time to adapt, and time to persist. But this balance is not guaranteed everywhere. As we move inward toward the heart of the Milky Way, that stability begins to fade, and the environment grows more intense, hinting at forces far more powerful than anything we experience here. From our quiet position in the Orion Arm, the center of the Milky Way feels impossibly distant. Not just far away, but hidden. Between us and the galactic core lies a thick veil of dust and gas, dense enough to block visible light completely. For centuries, the heart of our galaxy was invisible. Not because it was empty, but because it was buried. Only when astronomers learned to observe the universe in radio waves and infrared light did the center begin to reveal itself. What they found was not calm. At the very core of the Milky Way, in a region packed with stars, energy, and motion, lies an object known as SagittariusA. It does not shine like a star. It cannot be seen directly, yet its presence is unmistakable. SagittariusA has a mass of about 4.3 million times that of the Sun, compressed into a region smaller than the orbit of Mercury. Nothing else known can explain such density. The strongest evidence comes from motion. Stars near the galactic center move at astonishing speeds, swinging around an invisible point as if tethered by an enormous gravitational anchor. Some complete their orbits in just a few decades, far faster than stars anywhere else in the galaxy. Their paths trace the outline of something massive, something compact, something exerting control over the surrounding space. This is why astronomers conclude that SagittariusA is a supermassive black hole. For decades, it remained a mathematical certainty, a solution that fit the data, but resisted direct confirmation. That changed with the Event Horizon Telescope. By linking radio observatories across the globe, the EHT effectively turned Earth into a single, planet-sized instrument. For the first time, astronomers were able to resolve the glowing ring of material surrounding the shadow of a black hole. In 2022, SagittariusA joined a very short list, a black hole whose immediate environment had been observed directly. The image did not show a monster tearing stars apart. It showed a boundary, a region where light itself bends and curves, trapped by gravity so intense that escape becomes impossible. Yet despite its name, SagittariusA is not constantly devouring the galaxy. It is relatively quiet, feeding slowly on surrounding material. But quiet does not mean harmless. The galactic center is a place of extremes. Magnetic fields twist violently. Radiation surges. Dense star clusters interact gravitationally. Energy flows outward from processes we are only beginning to understand. And through it all, SagittariusA remains at the center. Not as a tyrant, but as a reference point. Every orbit in the Milky Way, including our own, is ultimately shaped by the mass concentrated there. The galaxy rotates because the center exists. Its structure remembers that gravity, even from tens of thousands of light years away. SagittariusA is not something to fear at a distance like ours, but it is something to respect. It reminds us that beneath the calm patterns of spiral arms lies a core defined by physics at its most extreme. And while the evidence for a supermassive black hole is overwhelming, science rarely ends with certainty. The closer we look, the more questions emerge about spin, about structure, and about whether the center is exactly what we think it is. Because even the strongest evidence leaves room for doubt. SagittariusA is almost universally described as a supermassive black hole. And in most practical ways, it behaves like one. It has immense mass. It dominates the motion of nearby stars. It bends light and warps space in exactly the ways Einstein's equations predict. But understanding what sits at the center of the Milky Way also means asking how it behaves. One of the most important properties of a black hole is its spin, a measure of how fast it rotates. Spin is described on a scale from 0 to 1. 0 would mean no rotation at all. 1 would represent the theoretical maximum allowed by physics. Based on indirect measurements of motion, radiation, and magnetic structure, many models suggest that SagittariusA has a very high spin, with estimates commonly ranging between 0.84 and 0.96. That matters. A rapidly spinning black hole does not simply sit in space. It drags space-time itself around with it, a phenomenon known as frame dragging. In this regime, space and time are twisted together, forcing nearby matter and light to follow curved, spiraling paths. Light passing near the event horizon is bent dramatically through gravitational lensing, sometimes looping multiple times around the black hole before escaping. These effects can create faint, unstable features known as light rings, bright paths formed by photons orbiting temporarily before falling in or breaking free. The Event Horizon Telescope observations are consistent with many of these predictions. They show a glowing ring of hot material, distorted by motion, gravity, and rotation, surrounding a dark central region. Yet, even with these observations, important questions remain open. Some physicists have explored alternative models, not because black holes have failed, but because extreme environments invite careful scrutiny. Among these ideas are speculative proposals involving ultra-compact dark matter cores or other exotic configurations that could, in principle, mimic some black hole-like behavior without forming a classical event horizon. None of these alternatives currently explain the data better. But science allows them to exist as questions, not conclusions. One event that sharpened this discussion was the passage of the G2 cloud. G2 is a cloud of gas that moved dangerously close to SagittariusA beginning in the early 2010s. Initial predictions suggested it would be torn apart completely by tidal forces. Instead, G2 survived. It stretched, it distorted, but it was not shredded as dramatically as expected. Later analysis suggested G2 may contain a stellar core, or that magnetic effects helped hold it together. Still, its behavior reminded astronomers that the environment near the galactic center is more complex than simple models often assume. SagittariusA remains the best explanation for what lies at the Milky Way's heart. But it is not a solved object. Its spin, its feeding habits, its magnetic structure, and its long-term evolution are all active areas of research. What this teaches us is not uncertainty as weakness, but uncertainty as discipline. Science does not demand perfect answers. It demands careful ones. Even at the center of our galaxy, the most extreme place we know, we are still learning what it means to truly understand what we see. And to understand how the Milky Way became what it is today, we now have to step back in time. For most of human history, the Milky Way felt infinite. It was a glowing band across the sky. Beautiful, mysterious, and impossible to measure. The first serious attempt to understand its true size came in the early 20th century with the work of Harlow Shapley. Shapley studied globular clusters, ancient, tightly packed groups of stars that orbit the galaxy far beyond its visible disk. By mapping their distribution, he realized something revolutionary. The Milky Way was far larger than anyone had imagined. From those clusters, Shapley estimated a galactic diameter of roughly 100,000 light-years and showed that the Sun was not near the center, but far off to one side. Today, refined measurements place the Sun about 26,000 to 30,000 light-years from the galactic core, a quiet orbit in the outer regions of the disk. For a time, this seemed like the answer. The Milky Way was a large spiral galaxy, wide but finite, defined by the stars we could see. Then observations began to disagree. Stars in the outer regions of the galaxy were moving too fast. Their orbital speeds did not decline with distance from the center, the way gravity from visible matter alone would predict. Something else was there. Astronomers called it dark matter. Dark matter does not emit light, does not absorb it, and does not reflect it. We cannot see it directly, but we can feel its gravity. Models now suggest the Milky Way is embedded in a vast dark matter halo, a massive, invisible structure that extends far beyond the luminous disk. While the bright, star-filled portion of the galaxy spans about 100,000 light-years, the dark matter halo may extend out to nearly 2 million light-years. In that sense, the Milky Way is not just a spiral of stars. It is a gravitational entity far larger than its visible form. This extended mass explains why satellite galaxies remain bound, why stars orbit as they do, and why the galaxy holds together over billions of years. It also changes how we understand our place. We do not live inside a neatly defined island of stars. We live deep within a much larger gravitational structure, one that overlaps with others and blends gradually into intergalactic space. The Milky Way is also not alone. It is a member of the Local Group, a collection of more than 50 galaxies, including Andromeda and the Triangulum Galaxy, all bound together by gravity and dark matter. As a whole, this group is moving through the universe at about 600 kilometers per second relative to the cosmic microwave background, the afterglow of the Big Bang. Nothing about this system is static. The Milky Way grows, absorbs smaller galaxies, and reshapes itself over time. Its visible stars are only the surface expression of something much larger and deeper. The true size of the Milky Way is not defined by what we can see, but by what holds everything together. And once we understand that, another realization follows naturally. The Milky Way did not grow in isolation. Its history and its future is tied to encounters, mergers, and slow, inevitable interactions with other galaxies nearby. Because the story of our galaxy is also a story of connection. Galaxies do not stay the same forever. They grow, they change, and over immense spans of time, they merge. The Milky Way is no exception. For billions of years, our galaxy has been slowly increasing its mass by absorbing smaller neighbors. Astronomers have identified evidence of more than a dozen past mergers, including a major ancient event, with a large system sometimes referred to as Kraken, whose stars are now scattered throughout the Milky Way's halo. Even today, this process continues. The Milky Way is in the process of accreting the Canis Major dwarf galaxy, a small companion whose stars are gradually being stretched, pulled apart, and incorporated into our own. This is how large galaxies survive, not through stillness, but through slow accumulation. The most dramatic event in our future, however, lies much farther ahead. The Andromeda Galaxy, our nearest large neighbor, is moving toward us at roughly 250,000 miles per hour, about 10 kilometers per second. In approximately 4.5 billion years, the two galaxies will begin to collide. The word collision can sound violent, but in space, it means something different. Stars are separated by enormous distances. Even during a galactic merger, direct star-to-star collisions are extraordinarily rare. Instead, gravity reshapes orbits, elongates spiral arms, and transforms two galaxies into a single, larger system. From within, the night sky would change completely. Andromeda would grow brighter and larger, stretching across the sky over millions of years. Constellations would dissolve. New star patterns would slowly emerge. Yet even this transformation would unfold far too slowly to feel like an event. Closer to home, the fate of Earth is governed by something else. In about 4 billion years, the sun's increasing brightness will likely trigger a runaway greenhouse effect, making Earth's surface uninhabitable long before any galactic collision matters. And around 7.5 billion years from now, the sun will expand into a red giant, reshaping or possibly engulfing the inner solar system. These timelines are vast. They stretch so far beyond human history that they lose their emotional weight. They do not threaten tonight. They do not rush. They do not intrude. What they offer instead is perspective. The Milky Way has survived countless changes before us. It will survive changes long after us. Its spiral arms will fade. New stars will form. Old stars will die. Galaxies will merge. And eventually, even star formation itself will slow as the universe grows quieter. Nothing about this future is urgent. Nothing about it is personal, and that is precisely what makes it calming. Your place in this story is not at the beginning and not at the end. It is here, in a brief, stable moment, within a galaxy that is constantly evolving. The Milky Way will continue its long journey, reshaping itself over billions of years, colliding, absorbing, and drifting onward through the universe. And tonight, as all of that unfolds far beyond perception, you remain exactly where you need to be. Safe, still, at rest. The Milky Way will keep moving while you rest. After all the distances, the motions, and the immense scales we've traveled, what remains is something very simple. We are made of star matter, atoms forged in earlier generations of stars, existing briefly inside a galaxy that has been moving for billions of years. The Milky Way does not pause for us. It rotates slowly, carrying stars, planets, and clouds of gas along graceful paths we cannot feel. And yet, for a moment, we are here, not at the center, not at the edge, but in a calm corridor, far from the galaxy's most violent regions, long enough to look up, to wonder, and to understand just a little of where we are. You do not need to hold the whole universe in your mind. You do not need to follow every orbit or remember every number. Tonight, it is enough to know this. The galaxy is vast. It is active. It is alive with motion and change. But none of that requires your attention right now. The stars will keep forming. Galaxies will keep drifting. The Milky Way will continue its long, patient rotation, with or without our awareness. Your only task is simpler. Breathe slowly. Let your thoughts loosen their grip. Feel how small you are, not in a way that frightens, but in a way that frees. You are safe in this moment. The universe is doing its work without you. And tonight, you can rest while the Milky Way keeps turning.